Alright folks, we're going to get through the last few problems in chapter 18. A soap contains sodium laurate. If bath water contains 0.001 molar aqueous sodium laurate, what calcium concentration is going to be required to form soap scum in the form of calcium laurate? This is KSP for calcium laurate. But we know whatever conditions we have, that's going to need to be greater than KSP to form a precipitate, right? Because we're going to have calcium laurate. That's going to need to dissociate. Well, it doesn't need to dissociate. It needs to go in this direction. I'm just writing the formula for it here. I'm not going to be able to fit this, so I'm just going to write two laurates with a negative charge. So Q in the form, that's going to need to be greater than KSP, which is equal to 6 times 10 to the negative 13. That's going to need to be equal to some concentration of calcium times the concentration of laurate squared. And we can throw that in. And so let's see, KSP, that's going to be 6 times 10 to the negative 13. Of course, this is Q. I should write, actually. This is Q here. And Q is going to need to be greater than this. So the concentration of calcium times the concentration of laurate squared, which is 0.001 squared. That's got to be greater than this. We'll divide both sides by 0.001 squared. This will cancel. Now I'm ready to do some math. Okay, 6 times 10 to the negative 13. We're going to divide that by 0.001. I'm going to do that twice. Divide by 0.001 twice, and there we have it. 6 times 10 to the negative 7, the calcium concentration is going to need to exceed this in order to form soap scum in bath water with this concentration of sodium laurate. Alright, we've got 1.234 grams of solid calcium hydroxide placed in pure water at 25 Celsius. We're given the pH of the solution at 12.68, and we need to find KSP for calcium hydroxide. Let me go ahead and write the dissociation for solid calcium hydroxide. Of course, this is aqueous as well. And I think I'm going to draw out an ICE chart here. We're not going to worry about the solid. We're going to say we have no calcium and no hydroxide at the start. There will be a change that's going to occur if this is going to dissolve to get us to equilibrium. So let's see, we're going to have X amount of calcium and twice that amount of hydroxide. And so we'll have X and 2X at equilibrium. We don't know what KSP is, but I can say KSP is going to be the concentration of calcium, whatever that happens to be at equilibrium, times the concentration of hydroxide, whatever that happens to be at equilibrium. We need to square that. Well, I can find the concentration of hydroxide at equilibrium because I've got the pH. So let's do that. Let's see, pH plus POH, that's 14, isn't it? If I subtract pH from both sides, then I know my POH is going to be 14 minus the pH, which is 12.68. 14 minus 12.68, that's 1.32. Well, the hydroxide concentration, then, that's going to be 10 to the minus 1.32. What is that? Let's make it negative, 10 to the x. The hydroxide concentration, that's going to be 0.0479 molar. Let's see if this helps. What am I trying to find? I'm trying to find KSP. I have the hydroxide concentration. Okay, let's plug these guys in here. So KSP, that's going to be X for calcium times the quantity 2X squared for hydroxide. So that's going to be 2X and 2X times 2x is 4x squared times x, that's 4x cubed. So if I find x, I got to cube it and multiply it by 4, I'm home free. Hydroxide concentration, that's twice x. Aha! So I can say 2x, that's going to be 0.0479. If I divide both sides by 2, I get 0.0479. Let's divide that by 2. I got my value for x, 0.02395. So let's plug that in here. KSP is going to be 4 times 0.02395 cubed. That's my value for x. I need to cube it. I think I'm almost there. 0.02395. I don't see a button to cube it, so I'll just multiply it by itself. 0.02395, so that would be that square. Let's do it one more time. 0.02395. Now we'll multiply that by 4, and we get KSP is going to be, KSP is going to be equal to 5.5 times 10 to the negative 5th. Now we'll try this problem. We're going to find the solubility of barium fluoride in pure water, and then in a solution of 5 milligrams per milliliter of potassium fluoride, and we're given the KSP for the salt. This one should be easy. I've got solid barium fluoride that's dissociating into barium ion and 2 fluoride ions. Initial change equilibrium, we don't have to worry about the solid. We start with none of this and none of this. We gain X amount of this and twice X this. And so I'm going to get KSP, concentration of barium at equilibrium, times the concentration of fluoride squared at equilibrium should be, let's see, X for barium times 2x for fluoride, but I got to square it. That's got to be 4x cubed. Does it not? That's correct. So now I just set that equal to 4x cubed. That's going to be equal to 1.84 times 10 to the negative 7. I'm going to divide both sides by 4. And then I'm going to need to take the cube root of both sides. Ooh, that's a little messy, but we'll get x is going to be the cube root of this whole thing under the cube root sign. Let's see what that comes out to. So let's see. I'm going to take 1.84 times 10 to the negative 7. Is that right? Yeah, that is. That's 1.84 times 10 to the negative 7. I'm going to divide that by 4. And now I need to take the cube root of that whole thing. I got a cube root button right there. 0.00358 molar. That was fairly simple. Now we've got to find the solubility of barium fluoride in 5 milligram per liter potassium fluoride. It's going to be a little tougher. It's going to have the same form here, but they're going to have an initial concentration of fluoride. That's because the potassium fluoride, that's going to completely dissolve to potassium ions, which won't affect the equilibrium. But it will produce fluoride ions that will affect the equilibrium. We'll start with some value of fluoride ion rather than 0. So I need to find out what this concentration is in units of molarity. So let's see, 5 milligrams per liter. So 5.0 milligrams of Kf per milliliter of solution. Let's see, 1,000 milligrams is a gram, that's Kf, and I looked it up. 58 grams of Kf is a mole, and of course there's 1,000 mils in a liter. I'm finding the molar concentration of potassium fluoride, so I can find the molar concentration of fluoride to stick in here. Let's see what that is. 5 divided by 1,000 divide by 58 times 1,000. That doesn't seem like much. So the concentration of potassium fluoride, which of course since it's 1 to 1, is going to be the concentration of fluoride. That's going to be 0.0862 molar. So that means our problem is going to be a little different this time. Just a bit. So I'm going to write my barium fluoride solid. That's going to dissociate a little bit into barium ion and 2 fluoride ions. Initial change equilibrium. Don't worry about the solid. No barium to start with, but we just found in 5 milligram per liter potassium fluoride, there's going to be 0.0862 molar fluoride ion present. So we got to include that. 0.862. Okay. Let's write KSP here. What was KSP? It was given to me. KSP is 1.84 times 10 to the negative 7. And just up here, I'm going to write what we got before. So we got 0.00358 molar. That would have been X, which would have been barium. But both of these were 0. In this case, we should get something lower because the presence of fluoride should shift the equilibrium this way, and we're not going to get as much dissolved barium. Nevertheless, some barium will dissolve, twice that amount of fluoride will dissolve, and an equilibrium will have X amount of barium, and we will have 0.0862 plus 2X amount of fluoride. I can write my equilibrium expression, KSP. That's going to be my barium concentration. I hope you're okay with me just writing that's equal to X at equilibrium. I hope you're okay with me writing this squared at equilibrium. 0.0862 plus 2X. Oh, I got to square it. We're going to try to make the math a little easier on us here. We're going to say, you know what, 2X is going to be smaller than 5% of this. What is 5% of that? I've already got 0.0862. Let's here multiply by 0.05. So 2X is going to need to be less than 0.0043, where we've got a much tougher calculation to do. But in this case, I can put this in for KSP, 1.84 times 10 to the negative 7. That should be equal to X times 0.0862 squared. It's going to be close. Let's divide both sides by 0.0862 squared. This cancels this, and X is going to be equal to whatever this comes out to be. All right, let's try it. Here we go. 1.84 times 10 to the negative 7. We're going to divide that by 0.0862. And we're going to divide that by 0.0862. Oh, that's plenty low. So X comes out to be 0.0000248 molar. So the amount of barium that ends up getting dissolved in this case is much less than in pure water. All right, we're going to finish up chapter 18 with this problem. We're going to try to see if a precipitate of magnesium hydroxide is going to form if we mix 25 mils of 0.1 molar sodium hydroxide and 75 mils of 0.1 molar magnesium chloride. The salt that's going to form is magnesium, which is going to come from the magnesium chloride, magnesium hydroxide. The hydroxide is going to come from the sodium hydroxide. So I want to figure out what the concentration of hydroxide is going to be in the final mixture and the concentration of magnesium is going to be in the final mixture. So you'll notice I start with 0.1 molar sodium hydroxide, and I'm taking 25 mils of it, and I'm diluting it to 25 plus 75 mils. So I'm diluting it to 100. So really, yeah, I'll just take 25% of 0.1. That's going to be 0.025 molar sodium hydroxide, and I'm just interested in the hydroxide in the formation of magnesium hydroxide. So far, so good. Same kind of thing's going to happen here for magnesium chloride, right? I got 0.1 molar magnesium chloride. I'm just interested in the magnesium. I know I'm taking 75 mils of the magnesium chloride solution, but I'm diluting it to a total of 25 plus 75 mils, which is 100. 75 over 100, that's 0.75. 0.75 of this is going to be 0.075 molar magnesium. That'll be twice the concentration of chloride, but we're not interested in that, right? The only ions we're interested in the formation of the salt is the magnesium and the hydroxide. So I can calculate a value for Q after I mix all this together. Let's see what Q is going to be first. I just write it out. It makes me feel better. Let's see. I'm going to get magnesium ion dissolved, and I'm going to get twice hydroxide dissolved. So my Q, I'm going to need to take my magnesium concentration, and I'm going to need to take my hydroxide concentration and square it. So let's see, magnesium is going to be 0.075, and my hydroxide, that's going to be 0.025 squared. And if this is greater than, right, if Q is greater than K, we head in this direction and form the solid. So if this value is greater than this, it's going to form a precipitate. Let's see. Okay, 0.075 times 0.025 times 0.025. 1, 2, 3, 4, 5. I'm getting 4.7 times 10 to the negative 5. That's my value for Q. Here's my value for K. Is Q greater than K, or is Q less than K? Well, it's going to be greater than K, right? This is much, much less, like a million times bigger almost than this. Negative 5, negative 11. You know, you're going to have to add 6 to get to here in the exponent. So Q is much bigger. So because Q is greater than K, magnesium hydroxide solid precipitate forms. That's chapter 18, folks.